my KCET 2025 aspirants, so we are just left with few days for our final KCET examination. So I hope all of you are preparing really well, and in today's video we are going to discuss one of the most important high weightage topic, that is your coordination chemistry, okay, or coordination compounds. So I'll be giving you all the important topics that you need to revise from this chapter, and we will also be solving some previous year questions with this video, okay. So you'll be doing some concepts and some questions, concepts and questions. So a proper revision of this chapter will be done in this particular video, okay. So let us first see what all things we have in this particular lecture. So first we will talk about Werner's theory. So Werner's theory is very easy, but here from this particular concept we get a lot of questions in the exam. Next we have important definitions. So this is you should be knowing because questions can be asked from here as well. Nomenclature very important, isomerism very important, bonding theories, metal carbonyls, and applications of coordination compounds, okay. So these are the topics. First coming to weightage. So from the last years you can see 3-4 weightage is there. I told you this is a very high weightage topic. So this year also you can expect easily 3 to 4 questions from this particular chapter. So this is a must do topic, okay, and it is easy as well. Okay, before that I want to let you know about our Abhyas KCET 2025 test series. So students, how much ever you study, if you don't practice questions, if you don't write mock test, then you won't be able to perform good in the exam, right? So that is why we have launched the best test series in the market, that is our Abhyas test series, where you have 35 mock tests, which includes both part test and full length test for the subject physics, chemistry, maths and bio, okay. This test will cover your PU1 and PU2 syllabus completely based on the KCET pattern and KCET exam type, okay. And apart from this, you will also be getting detailed video solutions, and you will also have live doubt clarification classes where we teachers will come live and clear all your doubts regarding the test series. And one more important thing is this test, if you have seen our videos, we have given you a demo. If you attempt this test, you can know your accuracy, you can know your speed, which question you spend more time, which is your weak, and what is your rank with all the students who have attempted the test. So a real time evaluation of your preparation you can do. So definitely this is a must, and the most exciting part is if you purchase our test series and win and get a rank below 1000, then you can win up to rupees 1 lakh, okay. So this investment of rupees just 1498 is a very small amount if you want to get into the top colleges of Karnataka and assure top 1000 rank, right? Fine, so that was there. So if you want to buy the test series, please go to the description section, link is there. Already part test 2 is already live. Many of the students, 5000 plus students have already registered. So yes, definitely they are ahead of you in your in the KCET preparation. So please don't be behind. Go to the description section, click on the link given below and purchase the test series, okay. Now moving towards our first concept was a brief definition of what is a coordination compound. So coordination compound is something where you have metal atoms, you have neutral ligands or negatively charged molecules, okay. So there is a bond between them. Which type of bond? Coordinate bond is formed between them, okay. Now what do you mean by coordinate bond? We have ionic bond, we have covalent bond, we have coordinate bond. Now in any bond we need 2 electrons, okay. So if this 2 electrons, suppose there is a bond between A and B, okay. So if A donates 1 electron and B donates 1 electron and a bond is formed between A and B, then it is called covalent bond. But if between A and B a bond is formed but both the electrons are given by B alone, okay, then it is a coordinate bond and it is denoted by this arrow. So in this coordination complex, the metal is there and ligand is there, and between this metal ligand bond, the one which donates the electron is your ligand, okay. So ligand donates electrons to the metal and form a bond. Which type of bond? Coordinate bond. So these type of complexes where you have a metal and where you have a ligand and there is a coordinate bond between the metal and the ligand are called as your coordination complex. I hope this is clear. Now we will move towards the next important topic, that is Werner's theory, okay. So Werner's theory says that in a coordination complex, okay. So before you ask what is a coordination complex, so this one, a metal and a ligand is called, the combination of metal plus ligand is called as your coordination complex. Now Werner says that in a coordination complex there are two types of valency. One is your primary valency and the other one is your secondary valency. Now primary valency is satisfied by the negative ions, secondary valency is satisfied by both negative ions and neutral molecules. So basically if you try to understand primary valency, suppose I have a complex that is written like this, P any metal, I am just writing like this. Okay, this is a coordination complex. So primary valency is nothing but the oxidation state of the metal. Okay, and secondary valency is nothing but the coordination number of the metal. Coordination number means how many bonds the metal has formed in a particular complex, that is the coordination number. So if you see here we have 4 bonds, so the coordination number of platinum here is 4, and I can also say that the secondary valency of the metal is also 4. Okay, so we have two types of valencies, primary valencies and secondary valencies. Now one very important thing is, if you have something like this, one complex and some ions here, when you dissolve this compound in the water, the ions, the metal and the ligand present in the complex do not dissociate. It remains as one unit. Okay, this is completely one unit and X is another unit. Okay, so this one will, so the primary valencies of the metal or the oxidation state of the metal is satisfied only by the negative ions. I hope this is clear. What is primary valency, secondary valency? You must have studied this in the in your PU2 exam also. So very important concept here. Now here is a very important question. On the basis of the following observation made with the aqueous solutions, assign the secondary valency to the metals in the following compounds. So we have to find the secondary valency of the metals. Okay, secondary valency means we have to find the coordination number of the metals. Now if you see in the first one, when you take this compound, you have been given with the compound and the formula of the compound is this one. Okay, means this is the formula of the compound. When you add excess of AgNO3 to this solution, you found that how many moles of AgCl was produced? 2 moles of AgCl was produced. Now that indicates that, I told you, if any complex is there, it will not dissociate. Whatever is present outside, that will only react, or that will form the reaction. So now you can see that if I treat it with AgNO3, right, and I am getting AgCl precipitate, so basically that means this is something, chlorine must be present here, and this chlorine is reacting with this Ag. So how many moles of AgCl is produced? 2. So that means 2 chlorine are present outside. Okay, so I can write like this, 2 chlorine are present outside. Now if you see the total PdCl2 4NH3, so this chlorine is 2 chlorines are outside. So what is inside the complex? We have PdNH3 whole 4. Right, if I have now PdNH3 whole 4, what is the secondary valency of the metal? How many bonds it is forming? So this NH3 forms one bond with the metal. So there are 4 NH3, so 4 bonds will form. So the secondary valency of the metal here will be 4. Clear? Next, coming to here, we get again 2 moles of 2 moles of AgCl is formed. That means 2 chlorine will be outside again, and that means 6 H2O will be inside. So I will have the formula for the second one as like this. You have Ni, just a minute, yes, Ni H2O whole 6. Okay, NiH2O whole 6 Cl2. So now here you can see that the nickel is forming 6 bonds. So if it is forming 6 bonds, the coordination number of here, the secondary valency of nickel is 6. Now here you see PtCl4 2HCl, and the coordination number is 0. Sorry, I can say the number of AgCl moles formed is 0. That means no Cl is outside, all the Cl is inside, right? So you can write the complex like this, PtCl4 2HCl. Okay, whatever is the given, that is the correct formula. I can write it in this form. Next I have the secondary valency, again here will be 4. Next I have COCl3 4NH3, and the number of AgCl formed is 1. That means only 1 chlorine will be outside. So what formula I can write? COCl2 NH3 whole 4 and 1 Cl outside. So what is the coordination number? 4 and 2, here total 6. Now if you see here, there is 0, no moles of AgCl is there, right? All the chlorine are present inside. So we have PtCl2 NH3 whole 2. Okay, so if this is present, so all the chlorine is inside, so that cannot react with AgNO3, so that is why you can find that 0 number of AgCl is formed. So that is how the secondary valencies and primary valencies questions are asked in the examination. Now moving forward to the next topic, some important definitions you should be knowing, that is coordination entity, central atom, ligand, coordination number, oxidation number, homoleptic and heteroleptic complexes. So what are this? The first thing. So this is the thing that will define all the first 3 terms. This one, which is the metal, the transition metal atom, that is called as your central atom. The ligands that are present here, or the molecules which form bond with the metal and are present inside the square bracket, are called as your ligands. Now this whole species where you have the metal, the ligands and the square bracket, this whole thing is called as your coordination entity. Coordination entity or coordination sphere. Okay, this is correct. One second. Okay. So this whole thing is called as your coordination sphere, and 6 here is coordination number, I told you, because Fe is forming 6 bonds here. So the number of bonds formed by the central atom is your coordination number. So the coordination number here is 6. Now the ions which is present apart from the coordination sphere, means the ions which are present outside the square bracket, are called as your counter ions. Okay. So I hope this definition is clear. Now we will move to next one, what is your ligands. So ligands are something that we should be knowing. Just a minute. Yes, the first thing that you should be knowing about a ligand is denticity. Now denticity means you have a ligand, right? This ligand has how many atoms which can form bond with the metal. Okay, generally ligands are unidentate, means one ligand will have only one atom which can form bond with the metal, but there are also certain ligands which are like didentate. For example, you can see here, I'll give you an example of didentate ligand. One second. Okay, so for example, just a minute. Yeah, so now for example, we have a ligand that is CH2, CH2, NH2, NH2, okay, ethylene diamine. So here you see this NH2 also form bonds and this nitrogen also form bonds. Okay, so now both of them form bonds and the denticity of the ligand is 2. That means this ligand has 2 atoms which can form bond with the metal. Okay, so generally so that is what is denticity. Now we have here one example of this ligand. This ligand, if you see, we have 1, 2, 3, 4, 5 and 6. These are the 6 places from which the ligand can form bond, and all of them form bond together. Means when this ligand is binding to the metal, all these 6 sides form bond with the metal. So metal is forming 6 bonds here, but one ligand, but bonds formed are 6 because it has 6 donor atoms. So it is a hexadentate ligand. And another important thing about the ligand is ambidentate ligand. Now ambidentate ligand also has more than one donor site. Okay, here you can see 6 donor sites are there. Ambidentate ligand has also more than one donor site, but both of them, 2 donor sites, ambidentate ligand generally have 2 donor sites, and both of them do not form bond at the same time. Suppose there are 2 donor sites A and B. So if A is forming bond, B will not form. If B is forming bond, A will not form. Okay, so that is your ambidentate ligand. You can see the example here. You have here NO2, nitrito. So if nitrogen is forming bond with the metal, we call this nitrito N. Okay, and if you have here ONO, if oxygen is forming bond, here we call it nitrito O. Okay, so you can see that nitrogen is also available, oxygen is also available, but at one time only one atom is forming bond with the ligand. Similarly, we have here SCN, where S is forming bond, then we call it thiocyaneto S, and if N is forming bond, then we call it thiocyaneto N. Okay. Next, chelating ligands. So whenever these denticity means bidentate, didentate ligands form, so you have a ligand when both the sides are donor sides, they form bond with the metal, then they form a cyclic ring. Okay, a cyclic structure is formed, and that is nothing your chelating ligand or chelating structures. Clear? Next, we have here homoleptic and heteroleptic complex. So this is very simple. If you have one type of ligands, means metal is bonded to only one type of ligand, then we call it homoleptic complex. And if we have different types of ligand, you can see here you have NH3 and Cl, different types of ligand, then we call it heteroleptic complex. Okay. Okay, now we will do some previous year questions so that you can understand what we have studied, whether we are able to apply that in or not in the exam. So the complex hexaamine platinum fluor chloride will give dash number of ions on ionization. So once you have learned how to decode the nomenclature, you can draw the structure, but for now I'll tell you the structure. So you have hexaamine, means there are 4 amine groups, right? Hexaamine means there are 4 amino groups, right? And the metal is platinum. So I can write PT, okay, and I have 4 amino groups, okay, and what is the charge given? 4. Okay, so this is the structure. Now see, okay, chloride is there outside, so I will write Cl minus 1. So now when this one will crisscross, right? So we have this complex and we have a chloride ion as well. So when we when these two will form complexes, I will get a complex like this, PT NH3 whole 4 and Cl4. So the total number of ions produced here is 4 plus 1, 5. So that is option number C. I told you this one will not dissociate, this one will remain as it is in the solution, and you will get 4 chloride ions. So total 4 plus 1, 5 ions we will get. Okay. Next, addition of excess of AgNO3 to an aqueous solution of 1 mole of PdCl to 4NH3 gives 2 moles of AgCl. 2 moles of AgCl will form, that means 2 chlorine will be outside. Then we have PdNH3 whole 4 Cl2. Right. Now what will happen? The conductivity of this solution corresponds to, this is very important question. See here. So if I just if this compound will break, then what I will get? I will get one like this, NH3 whole 4 2 plus, and I'll get 2 Cl minus, means 2 chlorine ions. So I'll get 1 cation, right, 1 cation, right, and 2 anion. Right, you will get 1 cation and 2 anion. So these type of compounds where, so this is what type of electrolyte? This is called as 1:2 electrolyte, means the ratio of cation to anion is 1:2. So 1:2 electrolyte. Okay. Next, homoleptic complexes among the following are. This is very easy question. Homoleptic complex means all the ligands should be same. So you can see here all the ligands are same, C2O4. Here you can see different ligands, so this is not there. Here also you can see all the ligands are same. So 1 and 3, that is your option number C. Okay. Next, the coordination number of Fe and cobalt in the complex ions are. So here you have to understand, you have to remember certain things. C2O4, okay, this is 2 minus, this ligand is called as oxalato, okay, and it is a bidentate ligand. Means what? Means the C2O4 structure, if you remember, it is like this. You can just draw like this. Okay, so that means when a metal is there, okay, if this ligand is forming bond, this oxygen also forms bond, this oxygen also forms bond with the ligand. So that is why it is a bidentate ligand. That means each C2O4 will form 2 bond with metal. So there are how many C2O4? 3 C2O4. Each C2O4 is forming 2 bonds, so 3 C2O4 will form 6 bonds. So that is why if this one is there, Fe here has formed 6 bonds with 3 C2O4. right? So the coordination number of Fe will be 6, right? So I can eliminate the other two options. Here SCN is a monodentate ligand, means one atom here S or N, it is SCN, so thiocyanato can be S or N, both can be there, but any one will form at a bond, so it can be like this. SCN 4 times is present, okay, or you can have NCS also, but at a time only one bond is being formed, right? So cobalt will have 4 bonds, so its coordination number is 4. So the correct answer for this question will be option number C. Okay. Next, the coordination number and the oxidation state of the element M in the complex, this one are. So you have to find the coordination number and the oxidation state of the element. So first of all, if you see coordination number, I told you similar to C2O4. C2O4 will form 2 bonds. Similar to EN2. EN stands for this ligand, CH2, CH2, NH2, ethane 1,2-diamine. Okay, so this, suppose a metal is there and you have En ligand, then it will form 2 bonds. Each En will form 2 bonds. Here we have 2 En, so it will form 4 bonds. Here 1 C2O4, so it will form 2 bonds. So total 6 bonds are there. So the coordination number of the metal is definitely 6. We can eliminate these 2. The next thing here asked is the oxidation number of the metal. So if I want to calculate the oxidation number, so it is simple how you use in the redox chapter, how do you calculate the oxidation number, like that only you have to do. So let me take the oxidation number of metal as X. En, you can see it is a neutral ligand, so its charge is 0. Okay. Next, C2O4, when I draw the structure also I showed you, you can see that it has a charge of 2 minus, right? So C2O4 has a charge of -2. Then NO2 has a charge of -1. It is equal to 0. So if I solve this, I'll get X is equal to +3. So the charge of the metal here is +3. So the correct answer for this question will be option number C. Okay. Next, we'll go to the most important part, that is nomenclature. So here are so many rules regarding the nomenclature. I'll tell you the basic rule first. See, whenever you are naming a complex, you have 2 parts in that. One is your metal and one is your ligand, right? So when you are naming, so basically first of all, wait, okay, yes, so basically you have first, one is your cation, okay, and the anion part. Okay, so always you should start with the cation naming and then the anion naming. Okay, now it is possible that this cation is a normal counter ion. I have showed you the counter ion, right? For example, if you see this one, where is it? Sorry, just a minute. One second, yeah, this one. So you can see this part, this is which is written first, this is the cation, but this is not a complex. It is anion, it is cation. Cation is a normal ion, anion is a complex. So whatever it is, whether it is cation, anion, or it is complex, not complex, you don't have to worry about anything. The only thing that you have to keep in mind is the cation should be named first and then the anion. Okay, that's the first thing. Now when you are naming the complex, okay, whenever you are naming the complex, it has 2 parts. One is your metal, another is your ligand. So when you are naming the complex, the first thing you have to name is the ligand, and then you have to write the metal's name. So first all the ligand names should be written and then the metal name should be written. When you are writing the ligand name, suppose there is 3,4-L1, L2, L3, there are 3 ligands. Okay, so ligand's name should be written alphabetical order. Okay, the one which is, suppose amine is there, so amine will come first, then you have bromido, then bromine will come, then chlorine will come. So alphabetically order the ligand name should be written. After that you have to write the metal name, and once you have written the metal name, in the bracket you have to write the oxidation state of the metal. Okay, I'll do examples, it will be clear. So first we have to write the ligand name. So first you have to write cation, then anion. Then whether cation or anion, any one will be complex. So whenever you are naming the complex, you have to first write the ligands, then the metal, and then the oxidation state of the metal. One more thing here that you should keep in mind is, if the complex, in case the complex is an anion part, okay, if the complex is your anion part, in that case the metal name will end with ATE. Okay, if it is a complex is the cation part, then the direct metal name will be written, but if it is an anion part, then the name of the metal will end with ATE. Okay, so yes, now I think I will be telling you this is done. Okay, now you can see the different ligands and their name. For example, fluorine is named as fluorido, chlorine chlorido, bromine bromido, iodine iodido, sulfato hydroxo, cyano, oxalato, carbonato, acetato, oxo, peroxo and superoxo. And here if you have these ligands are generally not used, but NO2 and NO you can use. NO2 plus is nitronium ion. Here neutral ligands, NH3 is named as amine, H2O aqua, CO carbonyl, NO nitrosyl, O2 dioxygen, N2 dinitrogen, C2H5N pyridine, and this one is ethylene diamine. Okay, now we will do some questions. So you can see here there is no cation anion and there is only one ion here, so I have to just write down one ion here, right? So first I will write the ligand. So if you see, this is NH3, that means amine group. So A definitely will start first, then I have chlorine and then I have nitro group. Okay, so if I write like this, so first I will write how many amines are there? 2. So I will write diamine. Okay, next I have chlorine. So for chlorine you can write chloro or chlorido, both are correct, chloro or chlorido. So I will write, for example, chlorido. Diamine chlorido. Here NO2 group is nitrito N. Okay, if it is NO2 means nitrogen is forming the bond, then it is nitrito N, and if oxygen is forming the bond, it is nitrito O. So I will write here nitrito N. Okay, so I have written all the 3 ligands, then I will write the metal, and metal name is platinum. Just a minute. Platinum. Okay, now if you see in platinum, the oxidation state of nitrogen, sorry, in this compound, if I want to calculate the oxidation state of platinum, so let it be X. Okay, ammonia is a neutral ligand, so I can put 0 for this one. Chlorine is -1, NO2 is -1, that is equal to 0, so you will get platinum 2. Okay, now it is not mentioned anything plus minus, that means it is a neutral compound, so you have to just write out a platinum. Okay, next if you see here I have K3 and this one is there, right? So that means potassium is one part and this is the anion, so this is your cation part, this is your anion part. In the anion part the complex is there, right? So first I will write the cation. So whenever in cation, whenever the counter ions are there, only the name of the ion is written. You should not write tripotassium here, no, that is wrong, only the name of the ion. So I will write here simply potassium. Okay, cation is over, now anion. Under anion what I have to write? I have to write the name of the ligand first, right? This ligand is called as oxalato, right? So I have to use the word tri because 3 is there, so trioxalato. Okay, then you have the metal chromium, but will I write chromium or chromate? So I told you if the ligand is in anion part, sorry, if the complex is the anion part, then the metal name should end with ATE. So I have written chromate here. And if I just write down the oxidation state here, then it is 3 plus X minus 6 is equal to 0. So it is plus 3. Okay, so that is the name. Next one, if I want to write this one, here you can see this is the cation, this is the anion, right? So cation name I have to write here En. What is the name of this ligand? En. We have to use the word ethane 1,2-diamine. And whenever you are writing this ligand, if there is any 2 or 3 whatever number is there, it is represented as not bi-di. Here we use base trace like that. Okay, so you can see here it is chlorido, here it is En or ethylene diamine. So definitely first chlorido will come, then this one will come, but how much chlorine? We have 2 chlorines. So I will first write down dichlorido. Okay, next this ligand name is ethane 1,2-diamine, but for 2 you don't have to write di, you have to use the word bis. Bis in bracket, then you write ethane 1,2-diamine. Okay, then you have dichlorido bis ethane 1,2-diamine cobalt. Okay, after that, this is over. Cobalt oxidation state you have to write. So if I want to calculate, let it be X. This is -2, this is 0, -1 equal to 0. So it is cobalt 3. Okay, and here I have to write chloride. Okay, dichlorido bis ethane 1,2-diamine cobalt 3 chloride. That is the name. So you can see chloride when it is the counter ion, so just you have to write the name of the ion. Next one, if I solve here, CONH3 CO3Cl. Again you can see this is the cation part, this is the anion part. So first this is amine and this is carbonato. So amine definitely will come first, but we have 5 amines, so I will write pentaamine. Pentaamine. Okay, then we have here carbonato. Cobalt. Oxidation state of cobalt, this is X plus 0 minus 2 minus 1 is equal to 0. So that is cobalt 3. And then I have chloride. Okay, fine. Now if I see, the next thing that we have to know is isomerism. So all of you know what is the meaning of isomerism. Isomerism means they have the same molecular formula but different structures are there. Okay, so that is generally is called as your isomerism. Now isomerism is categorized into 2 types. One is your stereoisomerism, another is your structural isomerism. Again, under stereoisomerism we have geometrical isomerism and optical isomerism. Now geometrical isomerism is generally your cis and transform. Okay, and optical isomerism means the when 2 isomers are the optical isomerism means generally we are talking about here enantiomers. Okay, so might be little difficult, we will understand it in detail. So first of all, in our syllabus whatever we have, the coordination number of the metal will be generally 4 or 6, means metal can have either 4 bonds or metal can have either 6 bonds. Okay, so please keep this first in mind, that whatever syllabus, topics, chapters, compounds we are having, in that metal will have only 2 coordination number, that is either 4 or 6. Okay, while talking about isomerism, we will be asked questions from isomerism on these 2 coordination numbers only, 4 and 6, means metal will be forming 4 bonds and 6 bonds. So now if I talk about in geometrical isomerism, we have coordination number 4, we will see what type of isomerism it shows. Coordination number 6 shows what type of isomerism. Okay, so whenever the coordination number 4 is there, okay, what is the geometry possible? It is either square planar or tetrahedral. So that means if metal is forming 4 bonds, then that 4 bonds may be either in the form of a square planar or it can be formed in the form of a tetrahedral. Okay, so this is the thing. In coordination number 4 we have either square planar or tetrahedral. Now one of the very important thing that you should know, that in tetrahedral there is no isomerism. Okay, if the molecule is forming tetrahedral, then it will have no isomerism, means it will have particularly that one structure, you cannot have any other structure for that particular molecule. So but if it is a square planar molecule, then it can show geometrical isomerism. Okay, so if I see this one, okay, one second. Now in coordination number 6, if metal is forming coordination number 6, then we can have 2 types of complex here, MA4B2. A4 means A is one type of ligand, so 4 ligands of one type and 2 ligands of one type, this is possible, and MA2LL2. So if you see A2 here, again A is a monodentate ligand and LL is a bidentate ligand, so that means 2 into 2, 4, 5, 6, again coordination number is 6 here, right? This type of compounds we can find here, and MA3B3 we can find out. So to make this coordination number 6, what all possibilities we have? MA4B2 in our syllabus, MA2LL whole 2, MA3B3. So what all isomerisms are shown by these all things we will see now. So first is coordination number 4. I told you there are 2 geometries, square planar and tetrahedral, right? So square planar, you can see, for example, platinum is there. This compound is given PTNH3 whole 2 Cl2. So in this case, you can see that if the two chlorines are on the same side and two NH3 are on the same side, we call it as a cis geometry. If you have chlorines on the opposite side, NH3 on the opposite side, we call it as a trans geometry. Okay. Next, in tetrahedral, it does not show geometrical isomerism, so you don't have to worry here. Now we will move to next thing, that is coordination number 6. So in coordination number 6, I told you we have three categories. One is your MX4L2, MX2LL2, MX2, okay. Here this is your different one, that is MX3L3, or you can write down MLA3B3. Okay. So when you have MX4L2, means 4 ligands are of one type, 2 ligands are of the other type. So if you this one, so you can see an example here like a CONH3 whole 4 Cl2. So you can find that if 4 NH3 are in one plane and the chlorines are in the opposite plane, then we call it as a trans geometry. Now if the 4 NH3 groups, or you can say if the chlorines are adjacent to each other and the NH3 are adjacent to each other, then we call it as a cis geometry. Okay. So this is your cis and this is your trans. Now here if you see MX2LL2. So here this is your bidentate ligand, or you can say didentate ligand. So if the chlorines are on the opposite side and the EN are on the opposite side, this is your trans form. And here you can see the chlorine are adjacent, EN are adjacent, EN are adjacent, then it is your trans, it is your cis form, this is your trans form. Okay. Next, if I see here MA3B3 type, okay. So this is very much asked in the exam. MA3B3 type, you have another type of geometry, that is your facial and meridional. Facial means on one face of the octahedron, you can say that all the 3 ligands are present, and on the opposite face another ligand, 3 sets of ligand is present. And here you can see if on one plane, okay, this is your on one meridian, 3 ligands are present, then it is your meridional isomerism. Clear? Okay. Next, we'll move to optical isomerism. So if I have this type of optical isomerism in our syllabus, we get from the ligands of this type, MLL whole 3. Okay, MLL whole 3. That means ligand, there is, we have like this a structure and its mirror image. You can see these are non-superimposable mirror images, so they will show you isomerism. Another one which we have already seen in the geometrical isomerism, that is MLL2 and A2. So in this we have seen that there is cis and transform. So transform, if you see the transform here, if you draw its mirror image, they will be exactly superimposable on each other and it won't show any optical isomerism. But if I have this cis form, if you see this cis form and if I draw its mirror image, the mirror image is not exactly superimposable on this one. So this can show optical isomerism, and we have this compound example here. So one is dextrorotatory, one is levorotatory. So dextrorotatory means again what? The compound will rotate the light in clockwise direction, and levorotatory means it will rotate the light in anti-clockwise direction. Okay, fine. Now we'll go to structural isomerism. So this structural isomerism is of 4 types. We have linkage isomerism. So for linkage isomerism, I need one ambidentate ligand. So here if you see, when I write NO2, nitrogen is bonding, and now if I want to write the linkage isomerism of this one, it will be like this, whole 5. NO2 can form bond like ONO, okay, instead of NO2. Oh, sorry, this 2 is not required. Yes, and then we have Cl2. Okay, so this is called as linkage isomerism. Coordinate isomerism means you can see here cobalt is forming bond with NH3, here chromium is forming bond with Cn. So what happens if chromium comes here and cobalt comes here? So what will be the coordinate isomerism? Cr NH3 whole 6 COCN whole 6. This is your coordinate isomerism. Next, ionization isomerism means when you dissolve the complex in water, if you are getting different types of ions, then it is called as ionization isomerism. Now if you see, if I dissolve this one in the complex in the water, I will get this as one complex and bromine ion separately. But if I dissolve, just I will exchange these ions, I will find this complex and sulfate ion, right? So I am getting different products on dissolving, so this is called as ionization isomerism. Next, solvation isomerism is possible when you have water molecule. So you can see I can take this water molecule inside, I can take this water chlorine molecule outside. So that type of isomerism is called as your solvation isomerism. Okay. Next, some previous year questions from here. Number of stereoisomers exhibited by the given compound. Whenever it is asked stereoisomers, please remember it includes geometrical as well as optical isomerism. Okay. So if you see this molecule COEN hold to Cl2, I have this one structure, I can draw like this: CO, Cl, Cl, En, I am just writing like this. Okay. So you can see Cl are on opposite side, En on opposite side. This is my trans geometry. I can also draw the cis one for this one. So it is like this. Okay. Okay. So this is your cis form, right? Now what will happen if I draw its mirror image as well? So if you draw the mirror image of this one, you will get CO, Cl. Okay. So if I draw the mirror image of this one, this are your optical isomers, this and these are geometrical isomers. So the total number of isomers I have here is 3. Stereoisomers is 3. Next, FeNO2 whole 3 Cl3 and FeONO whole 3. So you can see NO2 and ONO, that is your ambidentate ligand, and they show what type of isomerism? Linkage isomerism. IUPAC name of the given compound. Okay. First I will name the cation. Here the complex itself is the cation. So first we have to name this one. Next, in the complex, first I have to name the ligands in the alphabetical order. So here first is amine group. So pentaamine group. Carbonato wrong. Here, okay. Here I have pentaamine. Here also I have pentaamine. Here also I have pentaamine. Okay. Next it is CO3. CO3 is called as carbonato. So I have carbonato here. I also have carbonato here. But here I don't find carbonato, directly cobalt is come, so we have eliminated this one. Next I got, next after that cobalt will come, right? After that cobaltate has been written here. So if you know that if it is a cationic complex, the name does not end with ATE. If it is an anionic complex, then the name will end with ATE. Here since it is a cationic complex, no ATE will be there, so this option is also wrong. The correct answer for this question will be option number A. Okay. Next, the formula. Okay, now the name is given, you have to derive the formula. This is a bit tricky. So you can see the formula of penta-aqua nitrato chromium 3 nitrate is, okay. So I always remember that first the complex, the first part is your cation part. So I can say that this part is your cation and this part is your anion. And we have penta-aqua, means 5 H2O should be there. Here I can see 6, I can remove. Here also I can see 6, I can remove. Here I can have 5, here also I can 5. Then you have nitrato. Nitrato, this is nitrito. Okay, NO2 is nitrito. Nitrato is NO3. So that is why this is also wrong. Correct answer is option number C here. Okay. Next, which of the following is able to show geometrical isomerism? Tetrahedral, we already discussed, tetrahedral does not show geometrical isomerism. Square planar of the type MA2B2 will show, okay, but this is MA3B, this one will also not show. MABCD can show geometrical isomerism, so correct answer is option number D. If MABCD means all the 4 ligands are different, we get 3 isomers, please remember this one, out of which we have 2 cis and 1 trans. Okay. Next we have coordination compounds. Okay, bonding theories will talk. Okay, So first one is bonding theories. What all things we have seen? There are two types of bonding theories that is discussed. One is your valence bond theory, another is your crystal field theory. Under crystal field theory, we will discuss in octa. I told you coordination number 6 and 4 is what we have the major thing. So how the crystal field theory works for coordination number 6? Octahedral means coordination number 6 and tetrahedral means coordination number 4. Okay, and then we will also talk about the color of the coordination compounds. Okay, so first coming to valence bond theory, don't have to go this much in detail. So valence bond theory, what happens is the valence orbitals, means the outer orbitals, undergo hybridization. Hybridization means undergo mixing to form new orbitals. Okay, so first thing what happens, whose valence orbitals? Metals valence orbitals. Metals valence orbitals undergo what? Mixing. What is this mixing? In scientifically or in more technical terms, how do we call this mixing? This is nothing but your hybridization. Undergo hybridization to form new orbitals. Which type of orbital? New hybrid orbitals. Okay, now this metal has now new hybrid orbitals, and these hybrid orbitals form bond with the ligands. Okay, who will form bond with the ligand? The hybrid orbitals, means you know whenever there is a bond formation, there is overlapping of the orbitals. So the ligand orbitals and the hybrid orbitals of the metals will form bond. That is called as hybridization. Okay, now you have to remember, I told you whenever the coordination number is 4, we have two types of hybridization possible, sp3 and dsp2. And when the coordination number is 5, we have sp3d. This is not asked in the exam, and the shape for sp3 is tetrahedral, for dsp2 it is square planar, and for 5 it is trigonal bipyramidal. When the coordination number is 6, we have sp3d2 or d2sp3, and in both the cases the shape is octahedral only. Okay, next you have to remember this table, or if you have already drawn, you should be knowing. I will explain only one here, others you have to try. Okay, so let me take the example of CONH3 whole 6 3 plus. Okay, first let us discuss about this one. CONH3 whole 6, or just a minute. Okay, fine. So I have here CONH3 whole 6 3 plus. You have written PU exam, you must be knowing this. So what is cobalt electronic configuration? 3d7 4s2. Cobalt in +3 oxidation state will be 3d6. Now if I draw this 3d6, okay, 1 2 3 4 5 and 6, I have 4 unpaired electrons, right? Yes, I have 4 unpaired electrons. Now what is happening here? NH3 is a strong field ligand. Now what is strong field ligand, weak field ligand, we will understand after some time. Now just remember, if we have a strong field ligand, then pairing of electrons will take place. Pairing of electron will take place. So what will happen? All these 4 electrons will pair up. So I have now, right, 1 2 3 4 and 5 6, 3d 4s, and I have 4p. Okay, now for, see, the orbitals of the, these are the orbitals of the metal, cobalt orbitals, they will undergo mixing and they will form new hybrid orbitals. So there are 6 NH3 groups are there, so 6 hybrid orbitals will form. So what will happen? This one will, D2sp3 will undergo hybridization. 6 orbitals will undergo hybridization and they will form 6 new orbitals, 1 2 3 4 5 and 6. Okay, 6 new hybrid orbitals are formed. Which type of orbitals? D2sp3. Okay, now NH3 ligand will donate the electrons here. So we have NH3 ligands, right? I'm just writing N for short. Okay, so NH3 ligands will donate the electrons here, right? Okay, so now what happens here is, you need to know about the things. So here you can see metals has no unpaired electron. So automatically if no unpaired electron is there, then it is diamagnetic. Its hybridization is what? D2sp3. What's the hybridization? D2sp3. Coordination number is 6. That means the geometry has to be octahedral, whether it is D2sp3 or sp3d2, it is geometry is octahedral. So these are the things that will be asked in the question. So if you take in the exam, if you don't prepare this, you will draw these many things, you will waste a lot of time. So that is why I have given you the summary that you should be remembering. So for this one I told you D2sp3 octahedral diamagnetic. For COF6, it is, if you draw it, you can just draw and check once. So sp3d2 octahedral and paramagnetic. NiCl4 sp3 hybridization is tetrahedral and it is paramagnetic. NiCN4 dsp2 means square planar and it is diamagnetic. Okay, so this you can draw the valence bond theory and check for all of them. I have given you a summary. Next we will go to the second bonding theory, that is your crystal field theory. Now what does crystal field theory says? What does valence bond theory says? First let me explain, then we'll, as I have already, in valence bond theory what happens, the concept is metals are there, ligands, its orbitals are there, these orbitals undergo hybridization and then they form bond with the metals. That is what is valence bond theory. Crystal field theory is completely different concept. Crystal field theory says that the metal and the ligand bond is completely ionic in nature. It is not a coordinate bond, it is a ionic bond. What happens when the ligand approaches a metal? We have a metal, okay, metal D, so which you can see that the D orbitals of the metals are involved in bonding. Okay, so whenever a ligand approaches a metal, the D electrons present in the metal face repulsion from the ligand electrons. When they face repulsion, what will happen? The D orbitals split. Okay, that is your crystal field splitting. So what is it saying? Metal ligand bond is considered to be ionic, arising purely from the electrostatic interactions between the metal ion and the ligand. When ligand approaches the d orbitals, they split due to repulsion. Okay, so d orbitals, 5 d orbitals are present in one level, they will split. How the splitting takes place, that depends whether it is octahedral or tetrahedral geometry. So splitting of the d orbitals depends on the strength of the ligands. Okay, so now this is what is the strength of the ligand. Means what? CO is the strongest ligand. Okay, that means if metal is there and CO is approaching to the metal, then metal d orbital will split like this. Okay, but if a weak ligand, like for example I minus is coming, which is a very weak ligand, then metal d orbital will split like this. You can see the difference. Okay, when the ligands are very strong, repulsion will be very strong, so the splitting will be higher. Okay, so that is the concept. So you should be knowing this series, please remember this one. At least you should be knowing first 5 elements, the last 5 elements, or at least you have an idea which are your weak ligands and which are your strong ligands. Okay, after this we will see how the crystal field splitting takes place in case of octahedral. I told you, so these 5 d orbitals are present. When the ligand approaches, their energy increases, and after that there is splitting of this d orbitals. So in case of octahedral, it is T2g and here it is Eg, means 3 orbitals comes to total 5, right? 3 orbitals come down and 2 orbitals go up. Which 3 orbitals come down? dxy, dyz and dzx. These 3 orbitals together are called as your T2g, and when they go up, you get dz square dx square minus y square. Okay, and these 2 orbitals are called as your Eg orbitals. Okay, yes, so that is the splitting here. Next you can see in the tetrahedral. Okay, here I have to, in something we have to do regarding electronic configuration. So I told you that the splitting depends on what? On the ligand. So suppose octahedral is there, we know that T2g will go, 3 orbitals will go down, 2 orbitals will go up. But what is the difference when a strong field ligand approaches and a weak field ligand approaches? We will see now how the configuration will differ. Very important, please listen. So I have this metal, 5 d orbitals are present, right? So just a minute, 1 2 3 4 5. Okay, now if a strong field ligand comes, it splits like this, where you have 3 orbitals here and 2 orbitals here. Now when you have a weak field ligand, it splits like this. Okay, right? Now suppose one D1 configuration is there. D1, 1 electron is here, that 1 electron will go here, that 1 electron will go here. In case of weak field ligand, and here it is strong field ligand, right? Next, if I have D2, here also D2, here also D2. Next, I have D3, here also D3, here also D3. Next, I have D4. Now, when I have D4, there is a chance that the fourth electron can go to the higher level, or it can pair up here also, right? It can pair up or go to the higher level, it can pair up, it can go to the higher level. Now, just imagine the fourth electron is there, okay? Just imagine that you are having means there are 3 rooms in the ground floor and 2 rooms in the 10th floor. Just imagine 10th floor. Fourth person comes to this building, okay? There is option to stay in, there's no lift in the apartment. Just imagine the situation like this. So there is option to have a double sharing room here and or else to have a single room here. So what the person will do? Generally, person might think that 10th floor climbing will require more energy every day. So let's not spend that. Let me adjust here, okay? And here the ground floor is there and the one single room is available in the first floor itself. So what the person will think, why to adjust here, only first floor I can get a more spacious room for myself. So let me go here. So whenever there is weak field ligand, the electron will go to the higher level. If it is a strong field ligand, the electron will pair up, okay? This is the fourth electron. Now coming to fifth electron, same, fifth person comes here, occupies here, it occupies here. Next, coming to sixth electron, it comes here. Here what about sixth electron? See, already here also there is pairing, here also it has to share. So why to go first floor, why can't I share in the ground floor itself? So this is the sixth one. Now if you see seventh one, seventh here, when the seventh person comes, even though it wants to pair, but there is no space and there is directly one room in the 10th floor itself. So it has to take a room here only, right? And here what, seventh one can still pair here. Next, eighth one will come here only, here eighth one will come here. Ninth, again here there is no space, so it will pair up here, here ninth will pair up, 10th and 10th. Getting? So if I want to just write down the configuration, I will write from D1, D2, D3, it is same. So from D4 to D7 there is difference, okay? D4, if it is a weak field ligand, so what will happen? The down are T2G, right? So it is T2G3 and EG1. And if it is a strong field ligand, what is the configuration? T2G4, okay? Next, for D5, it is T2G3 and EG2, and here it is T2G5. Next, here we have when we have sixth electron, so 3 plus 2 already it is filled, the fourth electron will be at the down, so T2G4, EG2, and here it will be T2G6. Next, for the seventh one, and here there will be T2G5, EG2, and here it will be T2G6, EG1. Next, for D8, again here there will be pairing, so it is T2G6, EG2, and here you can find T2G6, EG2, okay? 9 will be again here 3, here 3, 10, here 4, here 4, okay? So that is the difference. Now always remember, it is also represented in a different way. So if your delta O is less than the pairing energy, okay? Delta O is less than pairing energy. Delta O is less means splitting is less. If splitting is less means the electrons will go to the higher level instead of choosing to pair. So when delta O is less than, then there will be no pairing of electrons. You can refer to this configuration. If delta O is greater than P, the very high difference is there, then there will be pairing. So there will be pairing in this case. So this is for weak field ligand, this is for strong field ligand. Clear? Okay. So next, in tetrahedral the splitting is always very low and generally it is E and T2, okay? So the reverse happens in case of tetrahedral geometry. Okay. Next, coming to color, so you can know that this splitting has taken place, right? D orbital electrons are now, the D orbitals itself has splitted. There is one lower energy level and one higher energy level. So whenever a radiation is given on this compound, these D electrons can absorb the energy can undergo a transition to the higher level and then can remit radiation and come back. So this DD transition takes place, because of which the transition element shows color, right? And for this DD transition, the most important thing is to have unpaired electrons. If all the electrons are paired, then there is no DD transition, okay? So first and the most important condition for this one is you should have DD transition, and for that you need to have unpaired electrons, okay? Fine. Next we have some questions here. Which of the following system in an octahedral complex has maximum unpaired electrons? Very good question. Very important question. So you should be very thorough with the electronic configuration. Now I told you the configuration will be different for D4 to D7. D1, D2, D3 and then D8, D9, D10 will have same configuration, both strong field and weak field ligand. So let us write down the configuration and revise. D9. Okay, so if I write D9 configuration, it is T2G and EG I am writing, right? So T2G down 3 orbitals are there, so each orbital will occupy 2, 2, so total 6 here, and EG will be 3 here, right? So how many unpaired electrons? Unpaired electrons here will be 1. Okay, if you just imagine like this, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So only 1 unpaired electron is there. Next, D6 low spin. Okay, D6 low spin. What is this low spin and high spin? So now see, whenever low spin is given, you should pair the electrons. Okay, low spin means you can imagine low spin means strong field ligand, where you have to pair the electrons. So D6 is there. So if I just write like this, D6 low spin means I have to strong field ligand, there will be very high splitting, so electrons will not go there, it will jump here only, it will pair up here only. So T2G 6 and N will be equal to 0 because there is no unpaired electron. D4 low spin, D4 low spin, again here I have to write, so that D4 low spin means pairing will take place 1, 2, 3 and 4. I have 2 unpaired electrons, right? So it is T2G are 4, right? And number of unpaired electrons here is 2. D7 high spin. So when D7 high spin is given, high spin means what? You should remember it is a weak field ligand, or I can say no pairing. Okay, strong field ligand, or here it is pairing. No pairing I have to do. Okay, so I can write 1, 2, 3, 4, 5, 6 and then 7. So total number of unpaired electron, what is the configuration I got? T2G 5, EG 2, and the number of unpaired electrons here is 3. So more is the number of unpaired electron, maximum unpaired electron is only asked, right? So the correct answer here will be option number D. Okay. Next, crystal field splitting energy of COCl6 is 18,000. The crystal field splitting for CFSC COCl4 is. So there is a relation between delta T and delta O, means tetrahedral splitting and octahedral splitting. What is it? Delta T is equal to 4 by 9 of delta O. So please remember this one. Okay. So if I just mention here, this is, you can see this is a octahedral, 6 coordination number octahedral, and it is asking for tetrahedral. So 4 by 9 of 18,000. So that is your 8,000. So option number A is the correct answer. Okay, next, for the crystal field splitting in octahedral B complexes, the energy of the EG orbital will decrease. So first of all, if you remember, the splitting is like this, T2G and we have EG, right? So here this is minus 2 by 5 and here it is plus 3 by 5. Okay, so the energy of the EG orbital will decrease. No, here this one is T2G and this one is EG. So EG orbital will increase, not decrease. So that is why this statement is wrong. Energy of EG orbitals will increase by 3 by 5 delta O, yes, and T2G will decrease by 2 by 5 delta O, yes. This is the correct statement. Okay. Next, correct order for the wavelength of the light absorbed in the complex ion is. So this is also very important question. See, when you are saying the correct order for the wavelength of light absorbed in the complex ions, when I have a very strong field ligand, what will happen? If I have a very strong field ligand, the splitting will be very high. This energy is high, right? So that means a light of high frequency will be absorbed, right? High energy light is required, and we know that E is equal to h nu. High energy light means high frequency light, and we also know that E is equal to hc by lambda. So if energy is very high, that means lambda will be short, right? So if the ligand is very strong, the lights of shorter wavelength will be absorbed. Clear? Now if I arrange the given ligands, we have NH3 and chlorine, here only NH3, here only Cl. So just let us have a quick review of our spectrochemical series that we have discussed, right? Where is it? Spectrochemical series, just a minute. Yeah. So you can see here that NH3 is there, Cn. So NH3 is a weaker ligand than Cn. Cn is a stronger ligand, right? So okay, just a minute. So students, now let us see the next question here. The correct order for the wavelength of the light absorbed in the complex ions are. So these are the complex ions given to you, and you have to find the correct order of the wavelength. Now just listen to the concept that is required here. So when you have a strong field ligand, the splitting will be more, right? When we have a strong field ligand, the splitting will be very high, okay? If the splitting is very high, the electron here will, if this energy gap is very high, then the electron present here will absorb a high energy radiation to go here, right? To get excited, it will require a high energy radiation. If high energy is there, that means it will also have high frequency, right? Because E is equal to h nu. If high frequency is there, then we also know that E is equal to hc by lambda. So more is energy, less will be the wavelength. So that means less wavelength. Okay. So now you see the ligand. So you have here NH3 and Cl. Here you have NH3 and here you have Cl. So the order ligand strength, ligand order is like this: NH3 and then Cn. You can check it in our spectrochemical series. So let me just show you the spectrochemical series that we have written. So where is it? Just a minute. Yeah. Yes. So you can see NH3 is a weaker field ligand than Cn here, right? So now if I go back to my question, okay, if I just solve it again, I'll show you. Yes. So now you see here there are 6 NH3 and here with the NH3 you also have a weak field ligand, that is chlorine. So if I consider the splitting, okay, if I just consider the splitting for 1, 2 and 3, 1 will have the least splitting, okay, so for 1, 2 will have better than 1 and 3 will have the most high energy splitting will be there. So if 3 is having the high and highest energy splitting, here the wavelength will be the least one. So I can say the wavelength order, okay, so it's not lambda, I'm sorry, the wavelength order will be 1 will be highest, then you will have 2 and then you will have 3, okay, or you can have 1, 2 and 3. So correct answer will be option number A here, okay. Next, the complex ion having minimum magnitude of delta O. Again, minimum magnitude of delta O means the weak field ligand, okay, the delta O, the splitting is very less. So just now we saw that Cn is a strong field ligand, NH3 is a strong field ligand, water is somewhere in between and chlorine is the weakest ligand here, okay. Again you can, can show you this spectrochemical series one more time so that you can have a correct idea. Okay, just a minute, again I missed it, yeah. So you can see here chlorine is there, then you have water, then you have NH3 and then you have Cn, right? So the weakest one is chlorine. So if chlorine is the weakest one, the splitting also will be the least in this particular case, okay. So correct answer will be your option number D. Now coming to the next concept, that is your metal carbonyls. So what is metal carbonyls? Whenever the metal is there and it is forming bond with carbonyl ligand, only carbonyl ligands are present, then we call it as a metal carbonyl. Now why do we are studying this metal carbonyl as a separate topic? I'll explain you in the next part, means in the next slide. So you can see some metal carbonyls example here, NiCO4, FeCO5. So please remember the structure here, questions can be asked. So NiCO4 is tetrahedral, FeCO5 is your trigonal bipyramidal. Here you have CO2, CO8. So please remember this carbonyl octacarbonyl cobalt structure. This is important. Here the questions is asked like how many CO bond is there. So any question can be asked. So please remember this structure. Next you have Mn2CO10, and here generally question is asked for bridging ligand. So you can see that this carbonyl and this carbonyl is the bridge present or is connecting these two cobalt atoms. So these are called as your bridging ligands. Okay, so please remember we have two bridging ligands here. Here there is no bridging ligand. So please remember the structure of these two compounds. Now coming to the metal carbonyls bonding. Okay, so generally what happens is metal and ligand, when bond is formed, ligand donates electrons to the metals and a sigma bond is formed between them. Generally a coordinate bond is present here, right? This is what all the ligands do. But what is extra present in carbonyl is one ligand to metal sigma bond is forming, and there is also a pi bond formed between metal and the carbonyl group. Okay, and due to this pi bond formation, the energy or the bond between M and CO ligand is very strong as compared to other ligands. Now what are the orbitals involved here, we have to understand. So first ligand will donate electron to the metal. So ligand from its orbital will donate electron in the empty d orbitals of the metal. Okay, when metal will donate electron to the carbonyl group, it will donate from its filled d orbital to the empty pi star orbital of CO. Please remember this one. So the sigma bond is formed by the donation of the lone pair of electrons on the carbonyl carbon. Okay, carbonyl carbon lone pair of electrons, whatever is present, to the vacant orbital of the metal. It is donating to the vacant orbital of the metal. You can see the sigma bond is formed here. For the pi bond formation, what happens? The donation of a pair of electrons from the filled d orbital of the metal into the vacant anti-bonding orbital of the carbon monoxide. So it donates from filled d orbital to vacant anti-bonding orbital. Okay. Next we have applications. So from questions can be asked from application as well, so I have to just revise the applications. So first of all, for hardness of water, which one is used, EDTA ligand is used, it forms complex with the metals. Then next important one is this one, where you have to know which metal is present in which compounds. So generally chlorophyll contains magnesium, your hemoglobin contains iron, and cyanocobalamin, which is your vitamin B12, from the name itself you can guess it contains cobalt. Okay, then you have to know this catalyst. This is your PH3 whole PRHCl. This is your Wilkinson catalyst. Okay, then in black and white photography you have you use this S2O3 complex, that you should be knowing. So next EDTA is used to solve the problem of lead poisoning. To cure tumors we use cisplatin. Okay, so these are some of the uses that you should be knowing. Okay, next some questions here. Which of the following is an organometallic compound? Organometallic means you have carbon as well as metal. Okay, so you can see here that this compound CH3CH2MgBr is an organometallic compound, or that is your Grignard reagent. Because why not this one? Because here there is no bond form. Okay, it is delta minus and this is a ionic compound form, but here actually a bond is formed. So CH3CH2MgBr. Here also it is a ionic compound, here also it is an ionic compound. Next, CO is a stronger ligand than Cl minus. Why? Just now we discussed, because CO can form even pi bonds. So option number B here. Next, select the most stable complex. Okay, so whenever stability comes, you should be knowing about something called as, we have discussed chelating ligands. Okay, means chelating ligands are those ligands which can form cyclic structures. Okay, And who can form cyclic structures? Cyclic structures can form by bidentate or polydentate ligands. Okay, so if in a complex you have more polydentate ligands, then it will form cyclic structure and it will be more stable. So here you can see there is no bidentate ligand or polydentate ligand, all are monodentate, so this is not stable. Here I can find two bidentate ligand, here I can find one, and here I can find three bidentate ligand. So here all the it is a complete cyclic structure, so definitely it will be more stable, so option number D here. Okay. Next, coordination compounds have greater importance in biological system. In this context, which of the following statement is correct? So, carboxypeptidase A is an enzyme that contains zinc. Hemoglobin is the red pigment of blood and contains iron. Cyanocobalamin is vitamin B12 and contains cobalt. Chloroform are generally green pigment in plants and contain calcium. Okay. So, okay, fine, sorry, this is asking about incorrect statement. Okay, so I did a mistake here. Is incorrect. So, we know that chlorophyll contains magnesium, not calcium. So, option number D is the correct answer. When this question is given, you can also learn about this particular enzyme, carboxypeptidase. It is an enzyme which contains zinc. Okay. Next, in FeCO5, the Fe and C bond possess sigma character, both sigma and pi character, ionic character, pi character. You know, whenever there is CO bond, it contains both sigma and pi. So, that is why option number B here. Okay. Next, this is a question, homework question. So, I want all of you to try this question and answer in the comment section. How is the MC pi bond is formed? Okay, we have discussed about the sigma bond, but how does the MC pi bond is formed? By donation of electron pair of half filled metal d orbital to empty. So, you can read the options and try this question. Okay. Next, yes, so that's all students. In this lecture I have covered all the important concepts from coordination chemistry, and I hope that this video will be a one shot video and you don't have to refer any other video. I'll be coming up with a very soon top 30 MCQs on coordination chemistry, so after you revise that, please do solve those questions. Okay, so that's all in this video students, and I hope it was helpful. Thank you for watching, and please remember we have to target 60 out of 60 in KCET chemistry, and we can definitely do it if we prepare hard. Okay, so do not worry, just stay calm and focus on your preparation. If you have any doubt, please put down in the comment section. So that's all students, and see you soon in the next class, and thank you for watching. Do not forget to subscribe the channel.